Hello, welcome back. We're going to continue our study of electrostatic fields in materials. And here we're talking about the continuity equation, which is a pretty neat thing. And I'm going to give you the punchline first. Here's the punchline. If we have a volume and it's got some charge distribution, rho v, in the volume, and if I inject via a current source some charge, so I place some charge in this volume, then it turns out what happens is that there's a decay of volume charge density. That means charge leaves the volume, and when charge leaves the volume, that means that there's a current in the volume. So if I just pump some charge in there, then there's a current. So that's basically the punchline of the continuity equation. Hopefully that whet your appetite. But now let's get there now. Let's get to the punchline. So let's start out by recalling from physics that charge cannot be created or destroyed. The rate of decrease of charge then within that given volume, I'll draw it again, the rate of decrease within that given volume must equal the current flux through the closed surface forming the volume. So we have a closed surface, S, around the volume, and then inside is the volume. So let me write that mathematically down. I've got minus d q enclosed dt equals the closed surface integral of j dot ds. I'll explain that. Remember, again, I said that the rate of decrease of charge within a given volume must equal the current flux through the closed surface because, again, charge cannot be created nor destroyed. So on the left, we have the rate of decrease of the charge that's enclosed in this thing. And then on the right, we have the current through the surface, or through the volume, I guess. Remember, the current is the integral of the current density, right? J. So the current flux through the surface of this closed surface making the volume is this closed surface integral of J dot ds. Now from the divergence theorem, which relates a closed surface integral with a volume integral, the right side of this equation is just the integral over the volume of the divergence of J. Hopefully you're pretty familiar with that now. You're pretty comfortable with that divergence theorem. We've applied it a couple times now. Now, since the enclosed charge, we can find the enclosed charge. All we do is a volume integral over the volume charge density. We can write the following: minus the derivative, so again Q enclosed, is the volume integral of rho v dv. Then I'll just use the right side of this equation from the divergence theorem, like this. And the left side, I can bring in the derivative, but if I do that, I have to make it a partial derivative because the volume charge density depends on x, y, and z, not only t. So I'm talking about the derivative versus t here. So I'm bringing that in as a partial. And I'll keep the left the same. Del does not get an arrow. Keep the left the same, or keep the right the same, excuse me. Now we've got two volume integrals, right? The left and the right, and they're over the same volume, and so we can compare the two integrands. And so we are left with the conclusion that the divergence of the charge density, or the divergence of the current density is equal to negative the partial derivative of the charge density versus t. This is the continuity equation. For steady currents, for which the rate of change in the charge density is 0, the divergence of J is equal to 0. And this is again for steady currents. Steady currents. And this is Kirchhoff's current law. Which you would have studied in circuit analysis class, but it looks a little bit different. It says the charge going in to any node is equal to the sum of the current going into a node is equal to the sum of the currents leaving the node. Okay. Now, with Ohm's law, remember Ohm's law in point form was that the current density was equal to the conductivity of the conductor times the electric field in the conductor. And with Gauss's law, I'll write Gauss's law with the electric field instead of the electric flux density, like this. And we're talking about epsilon here, so for any material this is true, not just free space now. Now if I take the divergence of both sides of Ohm's law, the top one, I have then the right side looks like this, and on the left side would be the divergence of J. Well, the divergence of J from the continuity equation is this thing, negative partial derivative of the volume charge density, right? But from Gauss's law, we've got this. Right? So if I plug in E is equal to, the divergence of E is equal to rho V over epsilon. Now I've got sigma rho V over epsilon, and then again from the continuity equation I have negative partial derivative of the volume charge density versus time. So this is actually a differential equation, and I can solve it with separation of variables. So I'll put the t's on the left, and I'll put the rho V on the right, like this. And then I just integrate both sides. So on the left, there are no t's hanging around, so that's just a constant, and I get sigma over epsilon times t. And then on the right, 1 over rho v, d rho v, that gives me a natural log of rho v. So and I've got the negative there. So this is negative natural log of rho v plus a constant of integration. I'm going to erase this. Okay, and then I'm going to express that constant of integration like this, e to the c, because e to a constant is just another constant. And I'm going to rearrange it just a little bit, solving for the volume charge density. And we can call this e to the c, we can call this a different constant. You'll see this is exponential decay. So I'm going to call that the initial volume charge density. So I'm going to give that constant e to the c, I'm going to call that rho v0, the initial volume charge density. And then this epsilon over sigma, that has to have units of time. So I'm going to call that capital T sub r. And so I'm left with this equation. So let's talk about this equation. So first of all, Tr, which is the permittivity of the material divided by its conductivity, we call this the relaxation time. And this is the equation. This is the punchline now. This is the equation that shows that the introduction of charge at the interior point, or at an interior point of the material, results in a decay of volume charge density, right? This is exponential decay. So I put some charge in there, and then the charge density changes. It decays with time. So that means that charge is leaving the material, it's decaying with time, and so that produces a current. The relaxation time is the amount of time it takes charge placed at the interior of the material to drop to roughly 37%, or e to the minus 1 of its initial value. So you see, if I plug in T is equal to TR into this equation, I have the initial value, the initial charge density, times e to the minus 1, and this is approximately 37% of the initial volume charge density, like this. That shows you what I just said was that the relaxation time is the amount of time it takes charge to drop to 37% of its initial value. So here's an interesting point now with this continuity equation. Let's talk about conductors. And feel free to pause the video. I want you to pause the video. Think about this. Should this relaxation time be long or short for conductors? Think about it. All right, well, hopefully you paused the video and you thought about it. Here's the answer. Conductors have a large, so for conductors, large conductivity, right? So what does that mean about the relaxation time? Well, if sigma is large, the denominator is large, that means TR is small. So, for example, for good conductors, TR might be roughly 10 to the minus 18 seconds, the relaxation time. Insulators, by the way, can have TR be something like 100 days. Okay, so that gives you kind of a feel of what, the discrepancy of what we're talking about here. Now, interestingly, perfect conductors, we talked a little bit about perfect conductors a couple of videos ago. Perfect conductors have sigma equal to infinity. So for perfect conductors, the relaxation time, is 0. So that means internal charge internal to the perfect conductor, is moved instantaneously. That's pretty neat, right? So let's think about that. If you had a voltage source and you connected a wire, right? You just shorted out the terminals of the voltage source. You're told never to do this. And if you assume the wire is a perfect conductor, which it's not, but if you assume it is, for a good approximation it is, then that means charge moves instantaneously throughout the conductor, throughout the wire. So if charge moves instantaneously, what's the current through the conductor then? The wire. Well, remember that current is the rate of change in charge. So if charge moves instantaneously through that perfect conductor, that means the current is infinity. And so how do you get infinite current? You blow up your voltage source basically. That's why you're told not to do that. Don't do that. So that's pretty neat, right? That we started with essentially Maxwell's equations, and now we're talking about the continuity equation, and in particular perfect conductors and how they can move charge instantaneously. Now in the next video we're going to continue our talk about electrostatic fields in materials, and we're going to now look at boundary conditions, or the interface between two different materials. So I'll see you then.